this is section 10.2, day 2, Pascal's Triangle and Binomial Expansion. So where we are is we're starting on page 692. That's really where we see Pascal's triangle written out. And it's written out in two different forms. We're actually going to talk about the second form first, and then we'll move on and we'll talk about the first form. But Pascal's triangle is named after Blaise Pascal, who lived in basically the early to mid 1600s. And he came up with a triangle that bears his name. And the way you construct Pascal's triangle is you create a triangle where you add one more number to each row as you work your way down. So you start with one number, then you have two numbers, then three numbers, four numbers, five numbers, etc. Okay, so it really does draw out a triangle for you. This triangle is made up of ones going down the edges. So you have ones all the way down. The in-between numbers are arrived at by adding the two numbers right above each of them. So for example, we need a third number right in the middle here. And the way that you get that third number is you take the two numbers right above it, one on the left side, one on the right side, and you add them together. What's 1 plus 1? 2. So that number is 2. Now, there are two numbers here that are missing, right, because we need four numbers in this row. So for this one, you're going to add these two numbers, which gives you, and for this one, you're going to add these two numbers, which gives you 3. And so you get 1, 3, 3, 1. The next row, you do the same thing. So 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 4 plus 6 is 10. 4 plus 1 is 5. This is how you construct Pascal's triangle. Seems like a totally random, arbitrary kind of structure, right? But it actually has a number of different applications. We're only going to talk about a couple of them. There's only one that we really care about today. One of the things that's really interesting about Pascal's triangle, I'm sorry, first of all, I need to tell you the rest of the structure. These going from left to right are rows. And so this is known as row 0, row 1, row 2, row 3, row 4, row 5, etc. So notice it starts with row 0, not row 1. Okay? Now, we also have diagonals. This is going down this way. All those ones is diagonal 0. And then diagonal 1, diagonal 2, etc. So diagonal 1, diagonal 0, diagonal 1, diagonal 2. Right, so diagonal 1 is the 1, 2, 3, 4, 5. Diagonal 2 is the 1, 3, 6, 10. Diagonal 3 is the 1, 4, 10, etc. You guys all get that? So we have rows and we have diagonals. Rows start on the left side and go across. Diagonals go diagonally down, starting on the right side. Okay, everybody got that? All right. What's really interesting, if we look at the rows, actually, you know what I'm going to do? I'm going to leave that there. Let's go to another screen. If we look at the rows, and this is not something we're going to use today, but I just want to show you that there are a number of different applications in mathematics for Pascal's triangle. This is row 0. And it turns out that each of the rows gives you a power of 11. So if we want to do 11 to the 0 power, 11 to the 0 power is equal to row 0, which is 1. if I look at row 1, that ends up being 11 to the first power. 11 to the first power is 11. There you go. There's 11. What's 11 squared? 121. 11 to the third power is row 3. It turns out 11 cubed happens to be 1,331. Row 4 happens to give us 11 to the fourth power, which is 14641, so 14,641. Now, when you get to row 5, for doing 11 to the fifth power, you start from the right. So the last number for 11 to the fifth power, because now we have some two-digit numbers, right? So what you do is you start all the way on the right. You have a 1. The next number over is a 4. The next number, I'm sorry, a 5, thank you. The next number over is 10. So what you do, it's like adding numbers, guys, right? If you have 29 plus 37, or let's say 31, 9 plus 1 is 10. You put down the 0 and you carry the 1, right? And you end up with 60. Same idea. This is 10, so we put down the 0 and we carry the 1 to the left. What's 10 plus 1? 11. So what do I put here? A 1, carry the 1. What's 5 and 1? And then we have a 1. And so 11 to the fifth power is 161,051. Pretty amazing for such a random seeming structure, right? But it does something far more amazing and far more useful to us in this particular chapter. And that is this. It turns out that all of the numbers in Pascal's triangle are all of our NCRs, where n is given by the row number and r is given by the diagonal number. So if we want to do something like 4C3, actually let's do 4C2. So what I would do is I would go to row 4, and I would go to diagonal 2, which is going down here, right, because it's diagonal 0, diagonal 1, diagonal 2. Diagonal 2 is here. Where do those two overlap each other? It turns out that 4C2 is equal to 6. To verify that, let's get our calculator out here. Go to my math menu. Go to my probability menu. 4C2. There we go. So that gives rise to the first picture on that page in the book, which shows you that another way of writing Pascal's triangle instead of 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, is 1 is row 0, diagonal 0. That's really 0, C, 0. Row 1, column 0 is 0, C, 1. Sorry, 1, C, 0, excuse me. Row 1, column 0 is right here. Row 1, column 1 is 1C1. This is then 2C0, 2C1, 2C2. So the 0C0 is 1, the 1C0 is 1, the 1C1 is 1, the 2C0 is 1, the 2C1 is 2, the 2C2 is 1. This one is really from 3C0, and then we have 3C1, 3C2, 3C3, etc. So that's your 1, 3, 3, 1. Do you guys see how that works? And it turns out that that holds for all of our NCR combinations. Pretty amazing. So what that means is that you have an option when you're using combinations, NCR, of rather than using a calculator, you could actually use the values from Pascal's triangle. Okay, questions about that? Yes, ma'am. Is it always out of 1, or do you mostly do other numbers? No, it's always 1s for Pascal's triangle. All right. So, why would we need to use so many of these things? I mean, it's pretty easy to just punch 3C1 into our calculator, right, to get that value. Well, what we're going to talk about now is we're going to talk about a use of multiple NCRs at the same time, and that is binomial expansion. And so what we're talking about doing here, guys, is we're talking about taking a binomial, which means a polynomial with two terms. And we're going to raise it to different powers and expand it out. So we're starting with just a generic binomial, some number a plus some number b. So what is a plus b, the whole thing raised to the 0 power, going to equal? 1. A plus b to the first power is going to be a plus b. A plus b squared, remember you can't just square the a and square the b. What do you have to do to this thing? What do you have to do? You have to FOIL it out, right? That's really a plus b times another a plus b, which ends up giving you a squared plus 2ab plus b squared. A plus b to the third power is a plus b times another a plus b times another a plus b. So you FOIL the first two out and you get this answer, and then you take each of those terms and distribute it through the last a plus b, and what you end up with is a to the third plus 3a squared b plus 3ab squared plus b to the third. And then finally, this one is 4 of those parentheses multiplied together. So you can FOIL the first two, and then distribute that into the third parentheses to get this, and then you take this and distribute it into the last parentheses, and it gives you a to the fourth plus 4 a to the third b plus 6 a squared b squared plus 4 a b to the third plus b to the fourth. So this you just get by FOILing repeatedly. The problem is, what happens when we have something like a plus b to the 17th power? You guys realize how long it would take us to FOIL all that out? And worse yet, what if we only wanted to know one particular term? We'd still have to find the entire thing, and it would take us forever. But I want you guys to pay careful attention to something. The first thing I want you to pay attention to is I want you to pay attention to what's happening with the letters. And an easy place to see it is if you look at this one in particular, we can see it really clearly. Notice that our power was 3. And what did we start out letter-wise on the first term? What did we start out with? A to the third power. What this tells us is we have this many exponents to go around. We have 3 powers to go around. We start out by attaching all of them to the a's, which means we really have b to what power? 0. But what is b to the 0? 1, right? So that's why it just disappears, because it just becomes a cubed times 1. Looking at just the letters, do you see that we go from all a's, 3 a's, to 2 a's and 1 b? What happened? Yeah, we traded in one of our a's for a b. Do you see that? Does everybody see what we did there? Does that pattern continue? So if I take my 2 a's and I trade one in for another b, I get a to the first, b to the second. And then finally, if I trade in my last a for a b, I get b to the third. Do you guys see that that also holds in all of these? For example, if you look at a plus b to the fourth, you start out with this many powers, they're all a's. Then you trade in an a and you get a b. Then you trade in another a and you get another b. Then you trade in another a and you get another b. And then you trade in the last a, so now you have all b's. Does everybody see what the powers always add up to? This power is 4. These add up to 4. These add up to 4. These add up to 4. This is 4, because the original was 4. 3. These add up to 3. These add up to 3. This is 3. 2. These add up to 2. This is 2. 1, 1. They both give us a 1. Do you see that? That the powers on A and B always add up to whatever the original power was on the original problem? Does everybody see that pattern on the letters? So what that allows us to do is that allows us to do things like a plus b to the fifth very easily, letter-wise. If I want to do a plus b to the fifth power, the first term is going to start out as what? A to the fifth. Okay? With some number in front of it, some coefficient. Then we're going to get some number times, what's the letter part going to be? A to the fourth, b to the first, plus something, a to the what? Third, b to the second, plus something, plus something, and then finally, plus something with all these. So do you guys see how easy it is to fill in that pattern with the letters? Any questions on that part? The only thing left for us to do now is to fill in the coefficients. I want you guys to look at the coefficients for a minute. When we had a plus b to the 0, we had a 1. When we had a plus b to the first, we had a 1 and a 1. Then we had a 1, a 2, and a 1. 1, 3, 3, 1. Do you guys see what's going on? What is it? It's Pascal's triangle. It's all of our NCRs. So what do you think is going to go here then? That's exactly right, guys. That's where you get the coefficients from. Comes from Pascal's triangle. If you want a plus b to the fifth power, the coefficients are going to come from row 5 of Pascal's triangle. If I go back to row 5 of Pascal's triangle, there's our 1, 5, 10, 10, 5, 1. If you want a plus b to the third, you go to row 3 of Pascal's triangle, 1, 3, 3, 1. There's our a plus b to the third, 1, 3, 3, 1. So that's where the coefficients come from. So do you guys see how we expand these so easily? You follow the pattern with the letters, and then you go back and you get the coefficients from Pascal's triangle. Now, the problem is, what happens if we're doing something like a plus b to the 17th power? Pascal's triangle gets cumbersome as it gets bigger and bigger and bigger. So there is another way to understand where to get these coefficients from. And it turns out that these coefficients, actually I can leave the numbers there. I'll do it underneath. The coefficients come from this. How many powers do we have to work with all together on this last problem? 5. So this is going to be 5 choose, and then we're going to decide how many of them we want to be A's. How many of those 5 powers did we glue onto our A? 5. So we're going to do 5 choose 5. 5 choose 5 is 1. Now we have 5 powers to use. How many of them are we going to choose for our A variable? 4. So this 5 comes from 5 choose 4. What do you think this is going to come from? 5 choose 3, because we want 3 of the 5 to be A's. And then 5 choose 2 A's. 5 choose 1 A. 5 choose what? 0 A's. That's where those come from. Does everybody understand that? Now, do I care which method you use to fill those in? No. In general, no. Which means on your homework tonight, they will ask you sometimes to use Pascal's triangle to do it. Other times they will ask you to use what is called the binomial theorem. The binomial expansion theorem. So let me actually just write it like this. The binomial expansion theorem uses the NCRs instead of Pascal's triangle. That's the only difference. Okay? When you guys are doing the homework tonight, I don't care which method you use. Even if the instructions say use Pascal's, if you would rather use the NCR, that's fine with me. If they say use the binomial expansion theorem and you would rather use Pascal's, that's fine with me. I don't care which way you do it. They're both equivalent to each other, so it makes no difference to me. Now, having said that, there is a reason why you need to know the binomial expansion theorem with NCRs. Okay, and I'll get to that in just a few minutes. But are there any questions so far? Okay. Does this seem easy enough? It is easy enough, guys. The only problem is, do you think they're always going to ask you to do a plus b to a power? Of course not. They're going to ask you to do things like this. They're going to ask you to expand 2x minus 3 to the fourth power. Please do not do the lazy mistake on this and just do 2x to the fourth minus 3 to the fourth. That will be wrong 100% of the time, guys. Don't even waste your pencil on that one. That will never be the right answer on these. Okay? What you need to do, the easiest way to do these, is to start by expanding a plus b to whatever power they're asking you to do. So we already did this one, right? This ends up being a to the fourth, right? Plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus 1b to the fourth, right? We saw that over here. This guy right here, the 14641. Is everybody with me on that? So you start with a plus b. That's why I showed it to you with a plus b. Start with the general one. Now, instead of a, what are we supposed to use in our actual problem? 2x. So what we're going to do is we're going to use this as our a. And what should we use instead of b? Negative 3. That's our b. And so what we're going to do now, guys, is we're going to go a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. Remember when we started I said those of you that do it the way I show you will find this super easy, and those of you that don't are going to have a miserable time with this? I'm showing you to use what when you go to plug things in here? Parentheses. If you don't use the parentheses, you're going to blow these. You're going to get them wrong time after time after time. What we now do, guys, is we now plug 2 x's in for all the a's in the parentheses. And we plug negative 3's in for all the b's. Everybody with me? All we have left to do now is simplify this, and we're done. Does everybody see how easy that is? But the parentheses are the key. So, when you do 2x to the fourth, what is 2 to the fourth power? 16. And x to the fourth power is x to the fourth. So that is just 16x to the fourth power. Now watch how I'm doing this, guys, because this will make your life easy. Notice now I have a 4. What is 2 to the third power? 8, and x cubed is just x cubed, times, what is negative 3 to the first power? Negative 3. I now need to put those together. Notice I have an x cubed. 4 times 8 is 32, times negative 3 is what? Negative 96. So that plus is going to now become minus 96. Does everybody see how I'm doing that? I'm simplifying it piece by piece up here, and then I put it all together down here. Do you see what happens if I leave these parentheses out? If you write it like that, are you going to come up with the right answer? You'll get the x to the third power, but what are you going to forget to cube? The 2. You're going to forget to cube the 2, and you're going to get the wrong answer, guaranteed. Don't make that mistake. Use the parentheses so you see that the 2 gets cubed also. If you do that, these are super easy. Next, I have a 6. What's 2 squared? 4. And then we have an x that gets squared. And then what's negative 3 squared? Positive 9. So we have an x squared. And we have 24 times 9, which is 182/16. So this becomes plus 216x squared. Does everybody see how easy that is? And you can use your calculator to help you do these things if you want. Plus, I have a 4, I have a 2x, and then what's negative 3 cubed? Negative 27. So that's going to give me 8 times negative 27 is, again, negative 216. And then we have an x. And then finally, negative 3 to the 4th is positive 81. There we go, guys. There's our answer. Do you see how easy that process is if you just do one part of it at a time? Does it take a little while? Yeah, but I'm not giving you that many problems. Okay? You guys are going to be doing like 10 problems tonight. And not all of them are full expansions. I'll show you what I mean by that in a minute. Does everybody have that copy now? That's the way I want you to do these. If you do it that way, these are easy. If you don't do it that way, you're probably going to get them all wrong on the test. It's typically what I see.
So the x's are supposed to go down?
The x's are going down each time because x is our a, right?
Yeah.
Now, if x was our b, then x would be going up each time, right?
Okay.
Right? The a and the b can be anything depending on what they give you in the original. So whatever the a's are going to go down and the b's are going to go up as we go from left to right. Okay? Any other questions on that before I show you a partial expansion? Okay. Now what they're going to do is they're going to give you something that looks like this. X plus 2 to the 17th power. But they're not going to ask you to expand the whole thing. They are going to ask you to find actually, let's do something bigger. Let's do the 11th. They want us to find the coefficient of x to the 11th in this expansion. So one of those terms, when we expand it all out, is going to have an x to the 11th power in it. Everybody got that? We want to know what number is attached to that x to the 11th power. Now, could you expand this whole thing to find it? Sure. Everybody's okay with doing that? Would it take a long time on this one? Absolutely. So let me show you that if you're just looking for one term, there's a nice shortcut. We know that somewhere there's going to be an x, which is our a to the 11th power. Our b is what here? 2. This is our a, and then this is our b, right, because we have a plus there. So that's going to be 2. What power, if this is to the 11th, what power does this have to be to? The 6th, right? You guys agree? Because these powers have to add up to 17. Now, the question is, what should go in front of it? Well, how many powers do we have to choose from? 17. How many of those are we going to choose to be a's? 11. Was that hard to set up? Now all we have to do is simplify this. Does everybody see what we did there? It's very, very easy to get the term that you want. It's not as simple to do this with Pascal's triangle. This is why you need to know how to do it with the NCRs. Because you don't want to have to do 17 or 37 or 120 rows of Pascal's triangle just to get one term that you could get immediately from using NCR. Does that make sense to everyone? Okay. So now let's punch this into our calculator. So we have 17 NCR 11, which is going to be pretty big. 1, 2, 3, 7, 6. 1, 2, 3, 7, 6. So that's the coefficient of x to the 11th, right? No. Because this is going to give us an actual number also, guys. What is 2 to the 6th power? 64. So what do we have to do to get the actual coefficient? Multiply the two number parts. So that's the last thing. So don't make that mistake on the test. That's one that gets people into trouble, is they forget to multiply it by that 64. They just give me 12,376 as the answer, when it's really 792064. times x to the 11th. So what is the actual answer to this question? The question that was actually asked of us. It's just the number, right? Because they didn't ask us for the whole term. They only asked us for the number, the coefficient. Any questions about that? Mm-hmm. Everybody see that? Because that's our b to the 6th power that has to go with a to the 11th power, right? Mm-hmm. Okay, let me show you one other variation on this, guys. Any questions on that one? Does everybody see how easy that is? If you do it the way I show you, these are really easy. If you don't do it the way I show you, you're on your own. Good luck with that. These things will drive you nuts. Because you'll make it into something very complicated. Because there's a lot of stuff going on here. But there's a pattern to it. If you follow the pattern, it's easy. Okay, the other thing they could ask us to do is they could give us something like x minus 3 to the 12th power, and they could ask us to find the 7th term. So again, we're only looking for one term. We want the 7th term. Now, I want you guys to go back for this pattern, and let's look at this again. If I pick a particular term, okay, first of all, the first term, and what I want you to do now is I want you to focus on B. The first term always has b to what power? 0. The second term always has b to what power? 1. The third term always has b to what power? What is it? The second, right? Sorry, I was pointing to the wrong one. This one, this one, this one, this one. So do you guys see that the power of b is always 1 less than the term number? Right? The first term has no b's. The second term has 1 b. You always have 1 less b than the term number, which means if I go to this problem, if I want the 7th term, how many b's am I going to have? 6. And since this is a 12, what must a be then? What power must a be? 6. And so what's going to go out in front here? Nope. 12, choose 6. 12 powers to work with. We're choosing 6 of them to be a's. So everybody see how that works? So you kind of focus on b for a minute here. You take 1 away from the term number, and that tells you how many b's you had, because you start out with 0 b's on the first term. Now, can we do this? Sure. This is 12c6. That's our calculator. 924. Times our a to the 6th power times our b to the 6th power. What's our a here? X. What's our b? So now I have to do negative 3 to the 6th. I have to do parentheses negative 3 to the 6th because the negative has to get raised to the 6th power also. 729. What's the last thing I have to do? Multiply the numbers, right? 924, 729. Our final answer, 673,596. 673,596, x to the 6th. That is the 7th term in this expansion. So using the binomial theorem makes it very easy to find the term that you're looking for when you're only looking for one term. Pascal's triangle is a lot more cumbersome there. So that's why it's good to know, if you're only going to know one, which one had you better know? The binomial expansion one, the one with the NCRs. But if you want to know both, that's great. And typically what I do, guys, is if I'm expanding something with the parentheses to the 5th or the 6th power, I might use Pascal's triangle. Anything bigger than that, I use the NCR. That's my typical rule of thumb. When I'm doing things on my own or making an answer key or whatever, that's typically what I'll do. Because I can write out the first 5 or 6 rows of Pascal's triangle in a matter of seconds. Right? Anything beyond that, I have to start kind of thinking about it more, and it takes longer, and it's just as easy to use my calculator to expand it. All right, questions about that?
How come the method used for the last one?
The method that, because we didn't know either one of these things to begin with, whereas on the last one, they told us that this guy had to be x to the 11. They gave us one of those two pieces. Does that make sense? This time they didn't. So we had to figure out what those two pieces had to be. That's the difference between the two problems. Other questions, guys? That's a very good question. Make sense? Okay, let me give you the homework.